Good afternoon. Welcome to Krishna's class. Continue with our discussion on Banach Spaces. It is worthwhile to spend an entire lecture or one or two lectures on some of the fascinating examples of Banach Spaces, but that is not my intention in this lecture. The intention of this lecture is when you take the P norm, there are some nice facts about the geometry, which it may be worthwhile to get an insight into it. And for that, we look at R2 with the P norm. So we take x to be equal to R2 over R. It's a two-dimensional vector space and it's a two-dimensional vector space. It's finite dimensional, therefore. And we define a class of spaces in the norm of x PB, right, is equal to P or 1 percent. And now maximum of odd x1 comma odd x2 this we designate by norm x infinity, norm infinity, where x is equal to the ordered pair x1 x2 So this is a typical element of R. Now the first thing that you observe is this, that for any P, and equal to infinity, defines a norm. Moreover, therefore x is a normal linear space. So for any P, it is a normal linear space. Okay. Now the question that you ask is it complete? It is complete because what you can do is if you take a sequence xn, okay, if you take a sequence xn, or n equal to 1 to infinity into so if the sequence xn is a Cauchy sequence, for any p, we can infer that xn1 and sequences. They are real Cauchy sequences. Since R is complete, these sequences converge to, and this is for any p. Okay? That's something which you can easily work with. That p and then find out what happens, what is the sequences converge to and respectively. So xn or xn1 and xn2, xn1 converges to x1 and xn2 converges to x2. Okay. Now we have the limit of xn. So R2 with P norm, this you call the P norm, is a complete so R2 over R with P norm is a complete normed linear space, that is they are Banach spaces. Now, to get an insight of geometric insight into the structure of the sphere, so it is immaterial which P you make use of. It is the entire R2, and that's a complete normed linear space. Therefore, they are all Banach spaces. Okay. Now one can also show that given P1 and P, these norms are equivalent. Okay. It's worthwhile to see how these arguments are made. Although I am not going to go to the details. Equivalent in the sense that if a sequence in converges in one norm, then it converges in the other norm of P that is, you can prove this, that is, if okay, where x is constants m which depends on and depends on positive constants. Such that this is to show that n and m depends on the value of p that you use, that is both p1 and p. Okay. So these are constants for which this is true. So that you see, if you take the corresponding metric, then you see that you can easily see that if a sequence converges in one metric, the sequence converges in P1 metric, then the sequence converges in P2 metric. So that I don't want to spend much time on that. But what is fascinating? I mean, see, the actual interest is not in infinite dimensional spaces where you see all these LP spaces are going to be different. In the finite dimensional case, they are all going to be the same. So whatever statements I have made here, they are equally valid for Rn. Okay, for Rn with the corresponding norms. Okay, so that is easy to easily, you can write down the corresponding norm and then work with it. Because in Rn, you will be using the norm, the norm P will be 1 by B, and so this gives the different norms that you have. So this for 1 less than or equal to P less than infinity, and this is the one for that is something which you can use and show that all these statements are equally well valid. So the Rn with these norms are all complete normed linear spaces, and therefore they are Banach spaces. But the moment you go to infinite dimensional case, this is going to be different. I shall not go into that, but before that, let me just, the objective of this talk is to essentially give a geometric picture of the unit ball, which will give some insight. Okay. Probably I have said this earlier in my earlier lectures in some other context, but let me just repeat it, doesn't matter. So we take R. We look at this space. Take X belonging to R2 with and write CP as this is equal to 1. Okay. For infinity and C infinity okay. So let us now, so what is the shape of put in inverted commas, because only in when P equal to 2, this circle looks a circle, the conventional circle. Otherwise, it has a different shape. Okay. So this is R2. Now take 1, 2. So minus 1, 3. Squares. Minus 1. These are 4 points that you mark. And you see that our traditional circle with radius 1 Yes. This is a traditional circle. It's a circle. Actually, a circle. It's the circle with center at origin and radius 1. Now, this we designate. This is the one corresponding P equal to 2. Okay, that is for P equal to 2, we have and norm x2 equal to 1. 1 is what I have. So I write P equal to 2 for that. Now you see that for P equal to 1, it is going to be norm x1 is going to be mod x1 plus mod x2. So this should be equal to 1. So when both x1 and x2 are positive, then you have or greater than or equal to 0, it is going to be x1 plus x2 equal to 1. x1 plus x2 equal to 1 is going to be this line. And then the other lines are when x2 is positive, x7 is negative. So you get a nice square. Okay, this corresponds to P. Now you see that when P equal to infinity, P equal to infinity, one this is the case where P equal. So this is P equal to 1, 2 and infinity. That is easy to see because you see that so this is equal to, if the maximum is x1 is equal to 1, mod x1 equal to 1 and mod x2 equal to 1. So you have these two lines and these two lines, and the norm x infinity is less than 1 is the region trapped between. So these are the lines. These are the lines. This is x2 equal to 1. This is x2 equal to minus 1. This line is x1 equal to x. These are the four. Whereas this is this line is, see, you have this is going to be minus x1 plus x2 equal to minus 1. This line is These are the 4 lines that, okay. So I will just mark them with a different color. So this is going to be the one for the value p equal to 1. This is for, okay, this is the unit circle in that case. And now I have used the word circle in inverted commas. This is the unit circle. Now this is the unit circle, the conventional unit circle, which is perfectly symmetric at the central point, and that we are familiar with in the Euclidean one. It is for p equal to 2. And then you have for p equal to infinity. Now I hope that much is clear. Once that much is clear, then you need some work with this. Now you see that you have 2 regions. One is p lies between infinity and 2. Then 1, okay. So if you take two regions, now you see this is the one corresponding to 2. This is the one corresponding to 1. This is the one corresponding to infinity. So for p less than 1 less than p less than 2 is going to be somewhere here. So this is a path like this, a convex path. Can actually draw this for some specific values and get convinced. Okay. So that is the one that you have, which let me mark with different color. So this is going to be for some p that lies between 1 and 2. Now this is the one that lies between 1 and 2. And then you have the situation where you have this one, so you see systematically this line has been bent to go through all these positions, okay, and in between it is bent to form a perfect circle when p equal to 2. Otherwise it lies between p lying between 1 and 2 here, as I have marked with yellow one, and the orange one I have marked the one that the boundary of the circle corresponding to value of p that lies between 2 and infinity. So these are the shapes of the unit ball or unit circle that you have in R2. Now one of the properties that you observe is that all these are convexes. Okay, so convexity is one of the common property that you have for all these unit circles. Okay, this unit circle in a way describes the geometry of the space. Okay, right? Okay. So neighborhoods of points are what you call circular neighborhoods or of points are going to be of this shape with the corresponding p. Taking the corresponding shape for the given. Okay, so this is one. This gives some insight into the space. But in R2, of course, you see that all these norms are equivalent, as I said, so it doesn't make sense. But when you go to LP spaces, that is infinite dimensional spaces, P norm, then of course the spaces would be different for different values of p, because some elements in some for a particular p may not be there in the other. Okay, so the spaces are going to be different, and that is the difference that you have. So you see that the problem becomes more complicated when you go to three-dimensional space. In all cases, you see that the unit circle or the unit disk that you get, the disk is the completely, having the entire region. So this is the disk. See, the unit disk is actually norm of whatever p less than or equal to 1. This is the disk. So this you can call dp. And dp, the boundary of dp is essentially cp. C infinity. Sorry, is cp. Okay, right? So these disks are going to be convex sets. This is what you have. These dp's are all convex sets. If you take the interior portion, so it's open convex sets. So that's about the structure of the LP now. Now, if you go to LP, one take LP such that is finite. So now automatically what you have, the expression that comes in the norm, the expression that you take for the norm, because that case you are taking the norm as Sn infinity, and L infinity the sequence Xn with or you take C. Is finite. Okay, in this case you write This is the norm. Okay, so LPR and L infinity are non-real spaces. And one can prove that complete with respect to the metric induced by the perspective. Now, what is significant is that one space may not be contained in. Okay. If you take two values for say P1 and P2, then some elements in LP1 may not be in LP. Okay. So they are not identical spaces. Okay. As sets, they may be different, and then you can actually work out the relationship between LP1 and L1 and okay, for various values of P1. But once again, see, although this picture does not make any relevance for that, but this will give you some insight into how the unit ball in these spaces would essentially look like. Okay, you are working out the unit ball. Now you can see that the unit ball for P equal to 1 is contained in the unit ball for P equal to 2. Or you see, if P1 then the unit is contained in L. This is one of the results that you can easily. Okay, as the same thing will be translated to the dimensional space. It is nice to have this kind of insight into how these Banach spaces are different. Now, of course, one can give a complete discussion on several examples of, say, Banach spaces. And of course, you can do the same sort of work on function spaces also with LP and the corresponding. Okay, so let me just conclude this lecture. It's a very short lecture to give some insight. I would carry on with it the next lecture and define what is a norm. What's a bounded linear map, and then how you form linear space out of bounded linear maps, and then what kind of or how do you give a natural norm with a norm. Okay, I think this short lecture that we can. Thank you very much.